Long time no see.
Oh, yeah, long time. It's been a while since we've been together in the same rectangle.
Yep. So this time, we are going to look at a summary of the forces we have learned so far. Very many forces, many fields. So now you have to make sure they don't blend together in your brain like a blender, because you will need
Yeah,
to
like
know the
GG.
difference. Okay, Miss Lee, let's look at the summary.
Okay, so we're comparing between the three force fields or the non-contact forces, which is gravitation, chapter 8, electric, chapter 17, magnetic, chapter 22. Okay, so you're just trying to put all these ideas together and make sure that you see how they are related and you can see how they are different to each other. So we're going to start with gravitational force first, which is the OG taiko, the one that we are very familiar with. Let's talk about properties first. This is always attractive. I don't care. You don't have to think polarity. You don't have to use this hand, use this hand. No, no hand to use. Always attractive. Very nice. Now, this one can be attractive or repulsive. So attractive and repulsive make sense in the perspective of electric field, electric force. But when it comes to magnetic force, I'm just going to draw a dotted line here and I'm like, do you use the term attractive and repulsive for magnetic force? No, you do left, right, up, down, into, out of the plane, or into and out of the screen. So many directions unknown. Okay. Next, we're going to look at what causes or what is the force proportional to. So for example, gravitational force, you must have mass for the force to act on you. So we can say force is proportional to the mass.
Miss,
Okay,
I got
because
a something, the idea. The
yes.
more mass you have, the more attractive you are.
Oh, is this the body acceptance movement?
Yes, correct. The more mass, the more
Yeah,
attractive. The bigger the force of attraction. Wow.
sure.
Okay, next one.
Oh, okay. Electric force is proportional to charge because you know the relationship F is equal to QE, right? So you can see when Q increase, F increase. Oh, all right. And magnetic force, I would say generally is proportional to current. Equations like magnetic force is BIL sine theta or BQV sine theta. Although Q and V is kind of showing that there's some current flowing inside your conductor, whether it's a slice like a Hall probe or a thin wire. So Haya, you look at these two, you see the equation so complicated now. You look at this, so clean, so nice. Why this one look like that one?
Isn't
This
there
is
a different version of those formulas? The KQQ over R square, the GMM over R. Isn't those more complicated? Why got two one? Why this one looks so simple?
you could
Hmm.
technically write this GMM over R square. But it kind of summarizes the fact that both of these forces obey the inverse square law. Okay. So the further you are, the weaker the force will be. Okay. So I chose the simpler equation because that defines the field. But of course, you can choose the basic or the law, like Coulomb's law and Newton's law equation, which is their origin story. So you can use the equation like F equal to mg and F equal to QE if you have the convenience of knowing what the value of G is and what the value of the electric field strength is, which oftentimes, if you've done enough past year question, you will notice that they will usually tell you or give you enough information. But in the chance, sometimes when they don't give you, then you default back to the origin equation, GMM or KQQ. So these expressions are used at level 1. Either you are trying to find two forces that you just met, you don't have a graph, you don't have any other information to draw from. But for magnetic force, you didn't start with a level 1 that you... Miss Ellie, we just roughly show them some stuff, right? We didn't tell them the whole origin story, right?
No, it's a bit more complicated, but it's okay. Well, someday you may see it if you go
Yeah,
into
someday when we
uni.
don't feel like A2 is breathing down our neck and you level up your maths, we will come back here. but today is not the day. So basically, magnetic field, we just show you some properties. You know, like how when you learn electric field, your science teacher show you some properties about charges, and then you feel very happy, something like that, lah. Okay, we don't go deep into the origin story of magnetic forces or magnetic fields. Okay, moving along. What about the medium? Gravitation is independent of medium. So your gravitational force inside water, in air, all the same. Okay, so independent of the type of medium. So sometimes paper 4 will ask you to compare any of these forces, which you can use any of these points as long as they are relevant. Okay, so both of these are dependent on medium. If you're wondering how you know, well, for electric field, you have your epsilon naught, which is your, what is it again, Miss Ellie? What is epsilon naught?
Free space? Oh, that's mu naught. What is E naught? Something something,
Then
a
we have
constant.
mu naught here.
Permittivity one is permittivity of free space.
So this is permittivity of free space.
Then the mu
This
is
is
what?
permeability.
Permittivity and permeability. Wow. Okay.
Free space.
These two constants you can find on the first page of every question paper in the data formula sheet, certain value there. So make sure you know how to find it lah when you're doing
Yeah.
calculation.
So I think the word permit, right, is because let's say there's a charge and it wants to set up a electric field based on whether you put the charge in oil or water or vacuum, that space or the medium will permit the field to be set up. Hence, they use the word permittivity. Permeability is, you know why? Because when you draw the magnetic lines, right, they look like they reach and curve in. So it permeates the space. So they use permeability. So if you're a kind of person like me that really enjoys language, I vibe with words like that. But if not, then you memorize or look at page 2 in your question paper. Okay, moving on. There are certain relative magnitudes of these forces. So you would have done questions like that in chapter 17. There's a past year question where you are asked to find the gravitational attraction between two protons and the electric repulsion between two protons, and then explain what is the third force, if you remember that past year question.
We got
So
make video about it.
we got,
God,
you got watch or not?
don't know leh. Okay, continue. Never mind.
Yeah,
You go and watch that.
yeah well, you're supposed to be our fan, go watch. Okay, so comparatively, these two forces are stronger, right? And let's talk about direction. So all this is a discussion about magnitudes. So think about all the videos that we have given you about state and explain, especially if they ask you to describe the forces. We describe the magnitude, and then we talk about direction. So gravitational force is parallel to the direction of your gravitational field strength. Electric force is also parallel to the direction of the electric field strength. But if you got use your left hand, this is perpendicular or 90-degree to your magnetic field. We didn't emphasize this in your syllabus, but all of these things are vectors. And if you do enough mathematics, you know that when you see a vector, you must treat it with respect and care. So this is just to tap that and remind you if you intend to study more of this later in your university life. And finally, this tool is independent on the velocity or the
So
motion.
don't care you're moving or not moving, you will still have that force act on you lah.
Same force, same direction, same magnitude, nothing will change. So I don't care whether you are jumping off a cliff or you are sitting, lying in the potential well on your bed, your weight or your gravitational force is still the same.
Okay.
But magnetic field always have to be that special third child, right?
How to describe?
This one depends on both the direction and magnitude of the velocity of the particle.
That's why it's so finicky. You have to use your left hand, check the direction, then you see how fast it's
Yeah,
moving, then it got different path, it curve. Hmm.
yeah. Sometimes, or if they move a certain way, the force can be zero, right?
Can. Which is very annoying. Ayo, the direction, just know how to use your left hand rule. That's it.
Mm. Just remember, if your left hand rule become a James Bond rule, these two parallel, no force now, okay? Left hand rule cannot be James Bond rule. All right, so this is a comparison of the forces. What else are we comparing next?
Maybe we
I
can
guess.
zoom in a bit to the comparison between how a charge behaves in a uniform field. So uniform E field, uniform B field. How the charge does its stuff inside there. Because we see a lot now. Charge in uniform electric field.
So these fields are uniform. Just going to add this in. Okay, so the force on the charge positive Q, I think I wrote the equation just now. Like this, right?
FQE or just FQE.
Stationary also QE long.
Or QE only.
Direction parallel to E.
Mm-hmm.
Okay,
Let's look at
so I
magnetic
guess
flux too, or path.
magnetic flux. Okay,
What's the
magnetic
force?
flux. FB.
VQV.
Sine
Sine
theta.
theta?
Hi. Okay. Stationary charge V0. What
So
happens to FB? Is there an
zero
equation?
also. You sub in a zero, the whole thing becomes zero already, so it's zero. Okay. Next. Oh, direction.
Perpendicular to B. Hiya. Hiya.
Okay, path followed. Let's draw out the
So
paths, the setup first.
so you can see that there are two parallel plates here where you can set up a uniform electric field. This is not news to you, okay? So the electric field will be directed from high potential positive plate to the lower potential negative plate. So normally you will draw your E like this lah, uniform separation. Very common AS question.
Mm-hmm.
Let's say I have a rogue charge, positive Q, joining the electric force. It will be obviously attracted to the negative plate, right? And it will follow the trajectory of a parabola.
Mm-hmm.
Okay, so the path followed here is parabolic. And if you again done enough past year by this point in your study, you will notice that sometimes they like to ask, explain why this one parabolic. Describe the path. Why is it parabolic?
The force, think about the force. Where's the force pointing?
Because of this one. That's why it's parabolic. The direction of the force. I
Maybe
zoom
we
in.
can draw a bit. Yes, we zoom in. So at every point inside the field hall, there will be this electric force pointing parallel to E, since it's a positive charge, so parallel to E. So everywhere you are, it's just F, all pointing to the left. Interesting. So because of that, then you have this parabolic shape, lor. I see.
Okay.
Hmm.
What about a beautiful magnetic field?
Okay, let's set up the magnetic field first.
Wow. Okay.
So here's the beautiful into the page magnetic field shaded bright pink. And we can usually we just label B and then we put an X there. And then the X just tells you you're going into the page. So you take your finger, you point at all 9X on the screen. So you poke.
Means I got one finger.
Oh. You take your pointing finger, then you point lah, you point
I
slowly, go
can't
and
point at 9 holes.
point one by one.
Okay.
That is into the screen, into the page.
Okay.
Okay, where's the
Great.
particle? Let's draw the particle in.
I think I'm just going to copy the same particle. Adventures of a positive charge. Level 2.
Okay.
V. So this one was also traveling at V before it enters the field. Time to use left hand, right?
Yes.
So index finger going in. Step 2, middle finger.
Point up.
Follow positive charge. Where is your thumb? Very much like Beyonce, your thumb is pointing to the left. So this is the direction of FB. I guess I better label this one as FE in case you're confused. So this particle will begin to turn, right?
Make a nice,
The
what
path,
they call it, arc of a circle. Ah, that's what they always say in past year. Arc of a circle or circular path kind of thing. And it's
it
like
might
circular motion there.
it might look the same, but this is actually part of a circle. Something like this. Okay. Miss, must it be semicircle? Lah?
As long as it's an arc, it should be fine.
It depends on the radius, so you don't know. Can be. You draw semicircle? Okay. But why is the path different and why do we fixate on this? And by the way, once it exits the field, it will travel this way, okay? Tangential. Wait, sorry. Let me draw it properly. Tangential. In case you are asked to sketch inside and outside of the field, which is a recent past year question. 3 mark leh, you draw this black color arrow properly. Wow. Such bonus. 3 marks.
Okay.
Okay. So what about the direction of FB?
It keeps changing. It's like what we learn in the circular motion, the centripetal force thing, always pointing to the center of the path, and it's always perpendicular to the tangential velocity. So it's like, oh, this is a different kind of force. It keeps changing direction, which is very different from the electric force you saw just now on the left side. So there you have one.
The center of the circle
Mm-hmm.
is somewhere, okay, a bit chat. This one will be 90 degrees. Am I drawing correctly? Yeah.
Correct.
Okay. So all these forces are 90 degree. My circle a bit odd lah.
A bit too small lah, but never mind lah. Aiya, we get the idea lah. We see so many times now. You draw, I draw, all the example theory videos, so many.
Okay, let me label the term circular path.
So this one, remember arc of a circle or circular path. There's quite a few past year that ask you to explain why it's an arc of a circle. So you need to think of, how is the force pointing? Where is the force pointing? Go check out those past year because you will be required to explain why arc of a circle. Parabola. They usually don't ask, but sure, good to know. There was one AS question that asked, what is the path of electric field? Is it a circle or is it a parabola? And then I look at it, I'm like, wow. AS, you guys supposed to know already, but never mind. We know now the difference and why it's called parabola. Parabolic.
Well, basically in AS, if you've never seen before, you can assume that it's wrong. Lor.
Fair. Okay. Last one.
Energy. Work done now, guys. Got force, must talk about work done. Right? So energy gained by charge passing across field can be work done on or by the charge.
In past year, they like to use the word work got out of the charge. Work done.
I don't understand.
That's just the way they say it lah. Work got out.
Work can come in or not?
I don't know. It's just a very weird way to say. Anyway.
I mean, I learned physics. I'm still learning physics. Is this lah? But sure. Work got out is which one? On or by?
Opposite of work done on charge.
So it's work done by the charge. That's why the work went out.
Something like that, no?
Okay. Sure.
It's a weird term. How we calculate?
Q delta B.
Okay.
B is KQ over R, and then you know lah. Okay, go watch lecture videos from chapter 17.
Yes. Okay. How about magnetic field? Got work done lah. Charged particle move around here.
Got force lah. Sure got work done, right?
But got change in energy meh? Got potential energy got kinetic energy Kinetic we can calculate lah. We know the V is usually, it depends. Usually in this case, it's constant lah. If you're in a part of a circle. But then, so work done is 0 Really
So miss, you know the rail gun where they shoot, they apply a force on that conductor, and they shoot out the conductor, the conductor got kinetic energy, right? The kinetic energy come from where?
Don't know. So there's some kind of
Not the
energy
real
there, but then you look here, there's like no energy. So like, how to think of this thing?
I will draw a real gun set up just to explain. Current go like this. You know how to find the direction of magnetic field? Which hand do we use?
A right hand grip rule. The thumb.
Finger follow. Thumb go in. If you're wondering why we keep choosing to go in, it's because it's easier to record, okay?
Easier
Let's
to
just be
draw.
easier to draw. Okay. So let's say if I put a conductor here, now the current will flow down as well. Will flow down through the conductor. So if I use my left hand, thumb still going in, middle finger pointing down. Sorry, index finger going in, middle finger going down. Where's my thumb?
Point to the right.
Point to the right. So this rail gun will shoot upwards. So it will catapult or be shot to the right. If you have seen the demonstration videos, you can go and find rail gun on YouTube. Who is doing the work? Where the energy come from?
From the circuit, miss. Circuit
From the
got
circuit.
battery, ma. Battery got some work done. Don't know. Somehow there's a strange interaction between electricity and magnetic field.
You got it. There's a strange interaction between electricity and magnetic field. And this strange interaction is he who shall not be named in your A2 syllabus, or rather, it's too deep now, and we kind of don't want to talk about it anymore. You need a lot of maths, okay? And it's at a higher level of physics that we currently, this level don't cover. All right, so is there work done? Sure, but it's not as straightforward as, oh, electric PE decrease, KE increase, end of story. No, sorry guys, we gotta do some integration lah, some polar coordinates lah, some other maths lah. So this one, I would just, again, put question mark, question mark, question mark. Don't know yet. So the Miss Ellie's hypothesis would be, yeah, there's probably from the current, which is the only place you can draw energy from, but how does it draw energy from? And in what way? Don't know. Later lah, if you study more physics or if you do some engineering, I guess. I think the one last thing I want to talk about this railgun or magnetic field situation is, you know how when you are in AS, you learn waves and this thing called electromagnetic waves. So you got electric field and you got magnetic field. And here's the plot twist. They exist together all the time. They are like two sides of the same coin. You can't have electric field without magnetic field there. You can't have magnetic field without electric field there. And their interaction or their vibration can travel through a large range of distance. That's why you see some blue shift, red shift from some distant stars. So all these things are very, very cool, but also very, very complicated. Okay, so if you're interested in all of this, there's so many places you can Google and find more information on. Very interesting stuff. But yeah, and if you're wondering why we learn it separately, hopefully it's clear in this comparison video that there are certain fields which are more straightforward and easy to think about. There are certain fields which require a lot of mathematics, then your brain hang now, cannot think so easily, but they also exist at the same time. You know, it's like you invite this friend to a dinner party because you genuinely enjoy their company, but then their boyfriend a bit weird. But you also have to invite two of them together because they come in a pair. So like a bit like that lah. We have to help you understand that this is more complicated than it is, but also they are closely related and linked to each other in certain ways as well. All right. And am I missing out anything in this video?
Nope, looks pretty okay. I think that's it. So that's a comparison. Make sure you know how to think of them separately a bit. So,
but also have that big idea in mind. They are also the same.
They're related, but they're kind of separate, but they're related. So keep that in mind as you go forward. I think this is all the fields we know. We will not be learning any more fields. This is it.
Yeah, in physics lah.
Yes.
So this one is something extra for you to learn in university.
Okay, so that is all for the comparison video. See you guys in the next one.
Bye. Like, subscribe, all the things.